Hello everyone, I'm Thomas Oomen, Professor, Department of Geological and Mining Engineering and Sciences at Michigan Technological University. I welcome you all to the American Geosciences Institute Earth Day webinar series. My presentation is on landslide early warning in a data sparse region, challenges and way forward, the case of Idukki, Western Ghats in India. I would like to thank the Society of Exploration Geophysics, Geoscientists Without Border program for the financial support for this project. As shown in the map of India in red, Kerala is a southwestern coastal state of India situated between the Western Ghats on the east and the Arabian Sea on the west. Kerala is known for its beaches, houseboats, paddy fields, and tea gardens, making it a popular tourist destination. Kerala has 14 administrative districts, and Idukki is one of them and is shown in red in the map. Idukki district is a densely populated district with 1.1 million in population and density of 254 inhabitants per square kilometer. Bordering the Western Ghats, Idukki exhibits two physiographic divisions, Midlands and Highlands. When you look at the digital elevation model, you can see that most of Idukki can be classified as highlands because of the elevation being greater than 75 meters above mean sea level. The photograph shown on the slide shows the tea gardens of Idukki. Due to the high population density and relatively low flat terrain, people in Idukki are forced to move to the highlands, increasing anthropogenic stress on the slopes. Coupled with more than 4,000 millimeter annual rainfall, most of which occurs in a 5-month monsoon period from June to October, Idukki is a hotspot for frequent and intense rain-triggered landslides. An anomalously high rainfall event in 2018, ranging from the 1st of June to the 29th of August, with a departure of 36% above the average rainfall measure, triggered more than 4,700 landslides in Kerala. On the slide, you can see some pictures from this event, out of which 2,200 landslides occurred in the district of Idukki, which is about 47% of that event. After the 2018 event, some members of the project team had the opportunity to visit Idukki for a reconnaissance survey. During the visit to Idukki, the reconnaissance team saw how the recent tragedies had invoked a fear of rainfall in the hearts of the local community. This called for action. Something would have to be done to support this community and help alleviate this fear. In the case of rainfall-induced landslides, equipping the community with an early warning based on the rainfall threshold can be a valuable information to reduce the risk. Similar events have been happening in the years after. In 2019, the Kavalapara landslide killed 60 people and buried bodies at more than 50 meters in depth. In 2020, Pettimudi landslide caused 62 deaths, and in 2021, the Kuttikal landslide killed 24 people. In order to develop an early warning system, accurate rainfall data and a landslide model is required. But in Idukki, compounding the risk factor is the lack of robust data that makes efficient modeling of landslide and any credible attempt at their early warning highly challenging. The Idukki district only have 5 operational rain gauges for more than 4,000 square kilometers. There is also a lack of fine-scale geophysical data to develop accurate slope stability models. Considering this challenge, the project was formulated with 3 objectives. 1. Utilize geophysical investigation particularly electrical resistivity survey, to characterize the geotechnical and groundwater properties of the landslide-prone terrains in the Idukki district. Second, develop rain gauge network in Idukki that can be integrated with a satellite-based rainfall forecast system to obtain accurate rainfall estimates. And third, develop a landslide hazard nowcasting system utilizing the improved geotechnical, groundwater, and rainfall characteristics that can be utilized for reducing landslide risk in Idukki. As pointed out earlier, Idukki only has 5 rain gauges. In such sparse data situation, satellite-based rainfall estimate is something that can be utilized to get better spatial coverage. The commonly used satellite product is the Global Precipitation Measurement, which is a constellation of satellites by NASA and JAXA. The observations are combined together using an algorithm called iMerge. Our first step was to compare the rain gauge measured rainfall to the GPM estimates. We used the 5-day antecedent rainfall from August 18, 2018 for this comparison and is shown in the table. What we noticed was the GPM estimates significantly underpredicted the rainfall at each of the rain gauge locations. The underprediction ranged from 60 to 85%. For example, the first rain gauge station at Pyramid recorded 1,773 mm rainfall, whereas the satellite-based estimate for that location is only 259 mm. This is a difference of 1,513 mm or roughly 85% under prediction. This slide shows the location of the rain gauges in Idukki on the left and the GPM rainfall estimates on the right. The GPM rainfall estimates have 10 km by 10 km spatial resolution, but as shown in the previous slide, it significantly underpredicts the rainfall estimates. Considering the significant underprediction in the satellite estimate, the challenge for us was to find a solution to preserve the accuracy of the rain gauge data and the spatial variability of the satellite data. In order to address this challenge, we used an approach called conditional merging. Let me walk you through how the conditional merging is performed. You begin with the rainfall measured by the rain gauge and use a spatial interpolation technique such as kriging or inverse distance weighting to obtain an interpolated rain gauge estimate. In this case, we use the inverse distance weighting for the interpolation. Then you extract the GPM estimate of rainfall at the rain gauge locations. The extracted value is interpolated again using IDWI to obtain the interpolated GPM data. We then use the given formula where the interpolated GPM data is subtracted from original GPM data and the interpolated rain gauge data is added to it. In this slide, we will look at the benefit of conditional merging. This is a table very similar to the one that I showed previously, with the column 1 providing the rain gauge station location name, column 2 rain gauge measurements, column 3 the GPM value before conditional merging, column 4 difference between rain gauge and GPM, column 5 GPM value after conditional merging, and column 6 showing the difference between original rain gauge measurement and the conditionally merged GPM estimates through k-fold cross-validation. As you would notice, the conditional merging process was able to significantly reduce the difference between rain gauge and GPM rainfall estimate. This provided us a successful solution to improve the accuracy of the GPM estimates and obtain the spatial variation of rainfall in Idukki. In this slide, the first map from the left shows the rain gauge location and its Thiessen polygons. We then overlaid the 2,223 landslides from the 2018 event on the Thyssen polygon. We then evaluated the rainfall threshold based on the rain gauge data for each Thyssen polygon. We repeated this exercise, and this time, instead of using the rain gauge data, we used the conditionally merged GPM data. A comparison of this is shown in the table. Column 1 shows the rain gauge station location. Column 2, the number of landslides that occurred within the Thyssen polygon of that rain gauge in 2018. Column 3, the rain gauge threshold. The column 4, GPM threshold, min and max value within the Thyssen polygon, and column 5 shows the GPM range. So if we take the example of Idukki station, the one-day rainfall threshold could vary between 710 and 840 millimeter when we use the conditionally merged GPM. If we had just used the rain gauge threshold of 815 for this Thyssen polygon, and locations would have experienced landslide even as low as 710 mm. Therefore, by using this conditionally merged product, we are able to get a better estimate of the rainfall threshold. Thyssen polygon analysis also identified some large gaps in the data and the need for additional rain gauges. Based on the Thyssen polygon analysis, land use, and landslide susceptibility of the Idukki district, 8 additional rain gauges were installed. In this effort, we partnered with the Kerala State Disaster Management Agency to ensure that these stations are located in government premises and maintained by the agency beyond the life of this project. The red dots on the map shows the new rain gauge location, and the green dots the existing rain gauge location. The photograph shows the installation of one of these stations. These new stations are automated weather stations that provide temperature, humidity, and rainfall data every minute and accessible through the cloud. The video shows how these stations can be accessed through the web service. We now have access to this data and are working on improving the rainfall estimates from the GPM data utilizing all 13 rain gauge stations, the 8 new ones and the 5 old stations, and develop the rainfall threshold based on 2018, 2019 and 2020 landslide inventory for Idukki. We are also conducting geophysical survey in several locations in Idukki. The students from Tech and the University of Kerala have been performing these surveys, and the objective of these surveys is to characterize the geotechnical properties, groundwater levels at strategic locations. Previous studies have demonstrated the applicability of electrical resistivity survey to characterize lithological boundaries, water content, and shear strength to use for landslide hazard characterization, and we are following a similar approach. The basic principle for electrical resistivity is that the different materials offer different resistance to the flow of current. In our preliminary analysis of the geophysical survey, we have found low resistivity associated with areas with increase in moisture and some of the previous landslide locations. We also notice increases in resistivity associated with the decrease in moisture in the slope. We are evaluating the relation between this data and the satellite-based soil moisture estimates to derive an interpolated soil shear strength estimate for Idukki. Based on the shear strength and groundwater estimates from the geophysical survey, we plan to improve the landslide susceptibility map for Idukki. For the slope stability analysis, we use an infinite slope stability model developed in GIS environment and referred to as GIS TISA. The GIS TISA algorithm is an open access code available for use, and the following publications will provide details on these methods. The remaining work as part of this effort include computing the shear strength at critical locations in Idukki from electrical resistivity survey, incorporate those shear strength estimates to refine the slope stability model for Idukki using GIS TISA algorithm, and finally use the slope stability model and rainfall information to create an early warning system based on rainfall thresholds. I want to thank you for your attention and acknowledge the contribution of my doctoral student Vishnu Lekha, who carried out most of the work, University of Kerala students who helped in data collection and fieldwork, co-investigators Dr. Snehamoy Chatterjee from Michigan Tech and Dr. Sajin Kumar KS from the University of Kerala, and Shekhar Kuriakos and other staff of Kerala State Disaster Management Agency who provided support in getting local permissions for weather station installations and field activities.